Okay, so what we will do is we have two plans. One plan was to uh, continue a little bit on the hands-on and do an integrated, we lost it there, integrated power flow with a transmission distribution system. That's one part that we want to complete, if possible, today. And I want to send this as a take-home assignment. The other part is I wanted to show you some integrated power flow with simulation control as a discussion, which we call it as integrated optimal power flow and management of IBRs. So I want to show you some simulation platform and results associated with that. So so that is, we have a 1 hour is the plan for us, 2:30 to 3:30. So what I will do is I will show you some simulations in Simulink, not simulations, and how the blocks are situated. I will not able to run all the simulations, but I will show you some examples. Then what we will do is maybe around 3 or something, we will continue on our assignment, hands-on. So you have some break on hands-on. I was thinking first to continue on the hands-on. Do you want to do that first, or you want to listen and then do it? Because maybe I think you can, I thought you can listen and then you can do hands-on. You want to do hands-on now or at 3 o'clock? If you want to do hands-on now, raise your hands. Some gap is better, otherwise you just do it. Okay. All right. So that's what I thought too. So the integrated optimal power flow modeling approach requires for you to build models that integrates with power system management and the power system modeling. So power system management and modeling, you saw this figure before. In this figure, what we were doing was to develop power system model and power system management. So power system models are done in Simulink. Power system management can be done using Python, any other software that can be used for integration, right? So I'm going to show you an example. This is one of the research work. In this example, you have power system modeling done through optimal power flow. So this is an optimal power flow example. You know all the things in this optimal power flow. So if you look at it in the optimal power flow, you see SOCP, OPF objective. Do you know what an SOCP is? Yes? These are the questions for tomorrow. What is SOCP? What type of optimization framework? SOCP comes under what optimization group? It's under convex optimization. Okay. What is the full form of SOCP? Second order phone programming. That's a full form of SOCP. So SOCP is a part of convex optimization, and the full form of SOCP is second order phone program. So in any optimization, what are the two parts? You want to run an optimal power flow. What are the two basic equations? What are the two different type of constraints? So in here you will see, what are the one very common inequality constraint? What is one thing that you should make sure that you maintain on an electric grid? So what is the one very common inequality constraint? Why it is an inequality constraint? Yeah, because you don't want to maintain the voltage at one number. It's not possible. You want to maintain the voltage in a band. So the very one common inequality constraint is voltage constraint, and that inequality voltage constraint has got how many level? Upper level and lower level, or just upper level, or just lower level? Upper and lower, right? It's called upper bound and lower bound. What is the name of an inequality constraint that has got upper and lower bound at the same time? I might have mentioned this, but you might not have registered. I kind of think that it's called box constraint, because you're boxing upper and lower bound. Box constraint. Okay, box constraints are. So if I ask you a question, what is a box constraint? What is an example of box constraint in optimal power flow? Voltage is an example of box constraint. How about the generator power limits? Is that a box constraint? Power coming from the generator? Yeah, definitely you cannot go maximum, right? The power coming from the generator has a minimum level too. Yes, it has got a minimum level. So generator power meaning active power, is a box constraint. How about current in a line? Is there a box constraint? There is a thermal current capacity, high current, low current. If there is no current in the line, is there a problem? It's no problem. So the currents are not, so they are not box constraint. So just think like that. I'm just saying, I'm not saying people are already writing notes thinking that will come tomorrow. None of them may come tomorrow, but I'm just saying these are the things that are pieces that you should, these fundamental pieces you should keep in mind. Any research or anything what you do in real life, it's all based on these connections. You don't have to think about very high, detailed things, but so you can actually develop a power flow like this. See, but the power flow, when you are trying to implement it in real life, it doesn't have a value if you don't run the power flow continuously with respect to time, right? So now you run, after 10 minutes you run, another 10 minutes you then I think that power flow has a value, right? So if you are going to run it in an electric grid, you have to run the power flow multiple times. For running the power flow multiple times with the same number giving to the power flow, is there any value? No. So to run the power flow multiple times, what you have to do? You have to get something from the grid, then run the power flow. So you have to get some information from the grid, then the runs the power flow. If this information is same every time, morning, afternoon, then there is no point in running that. So can you tell me what one information you need to run the power flow? Not one. One of the main information you need to run the power flow, the electric grid. Load values. These are no-brainer. Load changes with respect to time. So you have to collect the load value. So we call that as like a feedback. You got to get that load value to run up. Can you tell me one other information you need to get from the power grid to run the optimal power flow if the power grid has DERs? I already showed you what the output of the DERs, right? Why? Output of the DER is also changing with respect to time. So because of intermittency, whatever, you need the DER output. So if you get the DER output and the load output, that is generally called as, from the same location, I have DER output and load output. That is generally called as DER output plus or minus load output is generally called as net load. Remember, net load positive or net load negative. So you collect that information of the variation of DER, variation of the load, right? Not difficult to visualize, right? Okay, you get that information and then you run the power, right? Is there anything else I need to run the power flow continuously? from the field other than node and the DERs? What do you think? You ran a power flow code now, so now you can think about it. What are the things you need to run the power flow? Any active power, reactive power, which is basically the load generation, which we talked about. Active power, reactive power we need. What else? Specified value and actual value for active power that we collected. Anything else? Okay. Can you tell me an equation for active power in a AC active power in terms of voltage? P is equal to VI cos theta. For a power flow, what is the equation for active power? Same equation. Why you want? No, it's not same equation. Injected power is equal to so 2 bus. What is the power go flowing between bus number 1 and 2? P12. P12, understand what you mean by P12. What is the equation? V1, V2 sine delta upon X. Yeah, that is a simplified equation, but that's not a delta. V1, V2 sine delta over X. Yeah, you can say. What is a real equation? Do you know that is a simplified equation? Yes. What is a real equation? Real equation, too much to think about. That's right. It's not too much. P12 is V1, V2, Y12 cosine delta 1 minus delta 2 plus theta 12. Right? So, equation is V1 what is V1? Well, it doesn't matter, but what is V1? Voltage is on V1 is a voltage on bus number 1. What is V2? Voltage is on bus number 2. What is Y12? Y12 is the inverse of the impedance between bus number 1 and bus number 2. What is delta 1? Angle of voltage is on bus number 1. What is delta 2? Angle of voltage is on voltage of bus number 2. What is theta 1 2? Angle of impedance between bus number 1. So this is the equation for a power flow. So if somebody asks you what is the equation for a power flow, this is difficult to remember. Forget about N bus, VI, VJ, that's something. It's not difficult, right? What happens if R equal to 0? If R equal to 0, what is theta 12? 90 degrees. What is Y12? So this equation will become Agreed? 1 over x12 is b12. This is 90 degree cos 90. It just happens to be sine, and sine delta 1 minus delta 2. Good. What happens if I say delta 1 minus delta 2 equal to delta? Then this P12 is V1, V2 over X12 sine delta. This one, if you plot between delta and P, you will get this relationship. And this is what we call it as power angle curve. So, so that is what one of you were saying. Oh, P12 is V1 V2 over X sine delta. That's a special condition of the general equation between power flowing between one and two. Good. So, what are we doing by running the power flow? We are trying to find this P12. If I want to, that P12 goes to P12 star, which is the value I want. The difference between this is called delta P12. I am trying to find this voltage, this angle to make this same. That is what you are doing with power flow. To look at it in a simple form, like no Jacobian, no several buses, no. You understand? That is what we are doing with the power flow. So now if you do that with the power flow, for doing that, we need this. That is what we call it as a net load, or net generation, or so basically P12 is dependent upon this PL sitting here, right? Because it's only one bus. The load power is what plus losses you have to. That's right. And these are the things that you get calculate. Okay. What else you need to know to solve this equation is what I was asking. What is remaining in this? Huh? Theta and Y or B or whatever it is. What is theta and V? What is that? What is that? What is theta and B? Where is that coming from in real system? Y bus. So in real system, there is no Y bus. But what is the physical component that makes the Y bus? Impedance of the line. So what do you need to solve the power flow? You need to know the impedance of the line. Okay. Not only the impedance of the line, you need to know the connections between the impedance of the line. Okay. Do you know what the name for the connection between the impedance of the line? So you should know power, should know net load. Net load, I write it because we are talking with IBR. If there is no IBR, no net load. You just have a load. Okay. So you should know the net load. What else do you know? What else do you should know? Right? Just not impedance, also connection of the impedance. Okay. So you need to know the line impedance. Is that enough? You need to know also the connection of impedance, right? What is the name for the connection of the impedance? Huh? Yeah, there is a specific name for it. Okay. It's called network topology. Network topology. How networks are connected. Okay? This is important. You need to know the network topology. So you may ask the question, if I am running the power flow every time, is the load changing? Is a DER, whatever, is that changing? How about network topology? It's fixed. It's not changing. Right? For a transmission system, that is almost true. It's fixed. But for a distribution system, many times it is not fixed. You know why? Because distribution network topology, always you try to probably open a switch, close a switch, some maintenance happened, something. So the topology is not fixed all the time. So it may be changing. So it's important to understand the topology, in which topology you are working. So for example, to connect with you, I don't know whether you can see this. The IEEE 123 bus system picture I showed you, there are some switches. I don't know whether you have noticed or not. Some switch opens and some. So those switches can. What happens if I put it in a capacitor to a bus and connect it? And sometimes it's not changing every time, but then obviously it changes, right? So the network topology and change impedance also changes. All right. So with that being said, what you do is you run the power flow. After you run the power flow, you send the signals from the power flow. What are the signals that you send from the power flow? What happens if after you run the power flow? What will you do? So your power flow or optimal power flow you run, you get voltages, right? If you want to change something in the field, what will you do? What are the things that you should send from the power flow to the field for the controllers to work? Let's think about it. We can send several things. You can send power that needs to be scheduled for DERs as like a set point. So you can send to the DER, hey, I need to generate 3 megawatt, because if you generate 3 megawatt, the losses are low. Some objective. So these are set points for the DER. Okay? Do you give a set point for the substation? Generally no, because substation is considered as a slack bus in that context, because you will put the power from the substation to support for the losses. So substation, then what else you can? Can you send the voltages to the distribution network to some place, saying that this is the voltage I get if you have the power run in this point. If you want to change the reactive power, then my voltage may be improved. So can you send that as a actual voltage for a specific point? Because actual voltage on a point you cannot measure, right? Because you need to have somebody to can do that too. So these are the inputs that goes to the field from the power flow or optimal power flow. So let's write it. So OPF or PF send a signal P set V actual to field and collect back P net, which includes PL PDER and network topology. Impedance, you don't have to send it back because impedances are going to be standard, constant, and then you keep it. So you don't have to send it back. Make sense? Are you following? This is how you can arrange a model running. So what will you do? If you want to test this in the lab, what do you need? You need a powerful or OPA that you run in a computer. You need a connection. Instead of field, you should have a model of the electric grid. Then you can run it. So it is more like a software on a computer that runs the power flow. You have a connection, send the signal to a model of the electric grid. Right? So this model of the electric grid you can develop based on whatever software you think that you should use. So if you are looking at a model of the electric grid that is doing controls of an inverter very fast, and you want to run that in real as a real system, you can use something like a real-time simulation platform. And we talked about a real-time simulation platform, OpenRT, RTDS. If you are running the power grid not in real time, but you wanted to do slow changes in the power grid, what happens? You can run the power grid model as a USTS kind of a model, which is developed in another computer and another MATLAB. You could run the dynamic models on a software, things like that. Okay? Now your interest is what your objective is your interest. Are you trying to develop new algorithm for real optimal power flow or power flow? Then that should be your case study of interest, not the other software or other model that you run. Okay. It's good so far. So what we have done is we looked at how you can develop. So every time, whether you have a model that is running in OpenRT and all that, and your job is controlling that model, you may not be working on sending signals from the MATLAB or some. You may be developing controllers inside that model. That's also your contribution. So whatever controllers you are developing is also can be your contribution. So it depends on what contributions you make. So what I will do now is I will show you some examples connecting to this topic. So the topic of our interest here is how do you integrate the integrated system connecting with real-time and optimal power flow and real-time optimal power flow to this. So what you have seen here is you have a real-time simulation model running with a MATLAB and you signal. So you see that green arrow and blue arrow is pretty much saying what we have discussed there, except for we don't have a topology part. Is that readable? Make sense? Understand, right? So in this model, you are actually going to set the set point for the DERs and different points located on the IEEE 123 bus system. I'll stand here and then just show report some of the results. So you're actually doing case studies, changing the percentage of the load, percent of DER, and then you're running the two algorithm, SOCP. What is SOCP? Second order cone programming. What is NLP? Nonlinear programming. So two type of writing it down. That will not come tomorrow. I will say. So NLP and second order cone programming, you have that output that is coming from there, and you can look at the bus number where the DERs are connected, and set points for each of those bus number can be generated from there. and that set point you can look at what will be the voltage profile on a 1 hour period location if these set points are implemented. Now that implementation is done in real-time simulator. So you send the set points to the real-time simulator, use that set point and you implement it. So you run that in a loop, your closed loop. Make sense? So it's a snapshot of the model. So this is not sure exactly the same, but this is something like that. You see the model that is mill. So this model you can utilize to find out what will be the values that you want. This is the model that you can see. Variable loads are seen in the color that is notated here, which is, so what we are doing is you are changing the loads with respect to time. So you are modeling the loads and changing the loads with respect to time. So when the load changes, you can get that feedback values back from the measurement points. And then voltage change. You can plot the voltage thing. Now you see this voltage change is high. This voltage change is high when the DR set points are given. The voltage is changing based on the DR set point, and that voltage you can control with another control loop for the voltage, which is the same platform you can utilize to control. So this is an example of voltage management where you are so in this system what we have done is a transmission network. The first part here is a transmission network. Have you seen such a transmission network model anywhere? Yes? No? Don't remember? Don't. Huh? Yeah. Have you seen that? That model is a very famous model which is used for several purposes. I'm talking about. Uh, I'm talking about. I'm talking about this. Have you seen such a model anywhere? No. Okay. How many of you have taken a course in power system stability? Anybody taken or taught about power system stability? It's a very famous model that is studied in general on electric grid on several places. It's an IEEE pre-machine 9 bus system model, we call it. Okay, so transmission. I think since you are not aware of it, I'm not going to talk too much. This is again like an IEEE system model, which you get it. Pre-machine. Yeah, you know a 6 bus system model? One time used, yeah. So there are two models that you study very extensively on transmission network. One is IEEE pre-machine 9 bus, and Kundur two-area system model. So it's a two-area model. So this is a three machine 9 bus is actually a real system, which is an aggregated representation of a real system in the part of the United States, some part, which has got a lot of oscillations between those. So it's basically used for oscillation study. So you have three machine there, and 9 bus. This model, what we are doing here, what is this? What are you doing? We are connecting what? A distribution network to that model to make an integrated transmission distribution network model. So that transmission distribution network model, well, distribution network. Oh, have you heard of this distribution network? This is another distribution network model which is very extensively used. This is the 13 bus distribution model which has unbalanced 3-phase, 2-phase, single phase unbalanced model. And then you have DERs connected in different points in the distribution network. So you can actually get the data, analyze the voltage profile, develop an OPF, compute the OPF, get to the output set points, and that set points can be sent to the models for controlling the power and the voltage. So this is an example of integrated T&E included analysis for control. So you can see some modeling of the system. So the distribution system is right here, and IBR is here, and the generators are here. So you can look at the conventional generator system. Somebody was asking about developing models for testing out studies with IBR problems like inertia. How do you develop the models basically? So we were just talking about. So you could develop an integrated model with and without generator. So in this case, there is a one generator, one IBR. So you have inertia with all generators. You can put IBR. So the inertia will go down, and the inertia less system reduced. You run with that system, nothing, no research. Just run, see what is the effect of inertia going down when you have a load change, like a frequency event on that. That itself is fun. So you make the model, but the model has to be realistic. Like for example, if you want to do the inertia study, you cannot put a synchronous generator with a voltage source. It's of no use. You put a synchronous generator with the complete synchronous generator dynamics, which is represented in. So, and that doesn't really need to be a fancy, like very large system. 9 bus, 13 bus, unbalanced property, all the three machine. One is voltage source, another one is synchronous generator. That's enough. And then you just change to IBR and see what happens. Forget about even IBR, just put all the generators there. Inside the generator, if you look at it, well, this is the governor. But if you look at it in the generator, there are inertia constants. Have you seen inertia constant in the generator parameter box like H, like inertia constant? Let's keep reducing that number. That also will do it. And then let's see what happens to that. And then you try to build in IBR, what happens. So then you start working on some controls on IBR. So all those things are. So I'm trying to one of the key part for this lecture is to tell you how you can make realistic models and how do you can integrate it realistic model to perform some of the things that we discussed earlier on the slide, some control aspects or something like that. I think that is one of the challenge too, which I'm seeing people really don't understand what to do and how to prepare. So the study that you are performing is not correct. You do some part study there. So that's one example. Then what else? Then so you can actually look at there's a fault and the synchronous machine is coming back and the IBR is added after removing the fault. Then we are looking at the transmission system and distribution system voltages and see what is the comparison of transmission system and distribution system voltage. So if you are looking at the IBR addition and transmission system bus voltages after the synchronous generator is added, you can see there is no change on the transmission system voltage. But if you look at the distribution system voltages, you will see the changes that happens on the distribution system voltage if there are IBRs connected before and after the fault. So that's something, so you can do that kind of study. Now you can study optimization based volt-to-hour control. If you implement the volt-to-hour control, what will happen to the voltage profiles? So what we have learned is basically the real-time implementation and analysis. I'm thinking whether I should. Yeah, I think let's stop here and then we have only 20 minutes for the integrated one. So you got a flavor on how this has been modeled and how it's been connected. So basically that is the idea that we want to talk about. Tomorrow what I will do, so what we have done so far, we looked at power flow, optimal power flow, we looked at modeling in dynamic models and looked at controls of IBRs with the dynamics model that is connected. How those controllers can be linked to the optimal power flow and power flow with the integrated loop and use and signal. Tomorrow we talked about controllers on the power grid. Tomorrow when we meet, we will talk about how those controllers are implemented inside IBR, which means IBR control. So at that time, I will also touch base a little bit about type of IBR controls called grid forming and grid following. I don't know whether you have heard about these grid forming and grid following controllers. I'll talk a little bit about it. I will also talk a little bit about type of grid forming controllers. Since you mentioned specifically about VSGs, I will show a little bit on that. We may not have a lot of time on that. So those controllers are on the IBR level. And so you will see how those controllers can help improve the grid stability overall. So that's the topic that I have in mind, that I kept it for an hour for tomorrow. Then we will do our analysis and test and all that. Good. So one thing is, I think we gave you a review on power flow, optimal power flow. Some fundamentals, some concepts related to control of IBR, volt-to-hour control, volt-to-hour watt control. What will the voltage control do? What will the reactive control do? What's the difference between reactive control, power control, and voltage control? You understood? What is the voltage control? Is just to maintain the voltage in the point and then you control. Reactive power control is to push the reactive power to the system, not necessarily to maintaining the voltage at that point. So that's the difference between reactive power and voltage control. What is a volt-to-hour control? You are looking at a voltage and then finding out what will be the VAR requirement for that voltage based on a relationship, based on a graph. So that is the volt to VAR control. So that's linked. And volt to VAR watt control. So we talked about that. We also talked about how we implement the controller in the field. We implement the controller in as a primary control, secondary control, and tertiary control. Right? The difference between primary, secondary, and tertiary control is the control hierarchy, where you control at what level, area control, substation level control, and local control. Right? It is also to do with the time, faster versus slower. Right? The tertiary controls. We talked about legacy systems, and we talked about legacy controllers. What is an example of a legacy control in power distribution system? Legacy controller. Legacy means not modern or not new, which is the IBRs and all. Legacy system means existing system without IBR integrated. What are the type of controllers in distribution system? Which without IBR, what are the type of control? What do you control in distribution system generally? What? What do you control in distribution system generally? Voltage. That's what you control in distribution system. We have talked about. What are the devices that you use to control the voltage in distribution system? Voltage regulators. Transformer is called OLTC. LTC or OLTC. What else? Capacitor bank is what is included. So these are legacy. So if I ask you name a legacy controller in a power distribution system, what do you control in a power distribution system? Voltage, right? Basically. What else we have? So the interaction with the legacy controllers. Basically, one of the legacy controllers is like a transformer taps, and when you are controlling with the DR, you are controlling the inverter to manage the voltage. Yeah, I mean, these are some general things which you talked about, and then specific equations. We are not going to talk about that obviously in general because they are very specific. What are the? How do you develop a real time OPF, and how do you develop the? How do you implement the control architecture connecting with real-time OPF. You do a real-time OPF in a MATLAB, some platform, you send the signal. What signals you send? Set points for the power, set point for the DERs and voltages. What signals you take? Load, net load, information back. So these are some takeaways. Logical level, understanding level takeaways. Other ones you can. So one thing what we want to do now is that so I'm going to give that as a homework assignment for the integrated power flow, right? Can you continue on the integrated? Have you done this? By the way, how far are you with this? Just want to catch up also on that. How many of you have completed transmission system? No. Okay. Still working. Huh? How is it working? Okay. You want to talk briefly about how you connect them, distribution system and transmission system. I think you already probably know it, but